especially for those of you who are students here, it might be useful to walk through them at a slower pace so that you can understand what people are talking about. Because, it was very useful, for example, for the paper I presented yesterday about transfer learning. It was also showing up in another paper where people apply this methodology to particle filter estimating DSE models. And this very much draws on the collaboration with Anton and Simon. So Simon could very well given this lecture by himself. In fact, he would do a better job. But I'm glad that he's here, so he would at least provide me multiple forms of support. All right, so I'm going to give you a kind of example just to motivate what we're thinking about here, right? I'm going to draw an example from finance, but you can kind of replace it with your favorite example, such as the Hank model. The example I'm going to draw is basically a very much kind of bread and butter computational challenging example in finance, which is calculating the value of an option. This model, by the way, is kind of an extension of the Black-Scholes model, or sometimes referred to as Black-Scholes and Merton model, especially if you're at MIT. It's basically extending the model to have stochastic volatility and jumps that are double exponential, which empirically have been documented to be an important feature of the data. Right? So you can see that there are jump components over here. Then there's this mean reverting square root process for the volatility. By the way, the volatility here will be a hidden state variable in case you get that. And then typical way of evaluating an option will be something like this, right? This is basically what I talked about yesterday, that in some cases, the function we're trying to approximate actually generically comes in as a form of expectation. So just like when we're doing like forecasting in the machine learning setting, we're trying to calculate something conditioned expectation, right? Given a set of features. Here, actually, the problem that comes in that we're trying to approximate already comes in that form, which actually is an important feature to keep in mind. Another thing is that this is kind of the terminal condition, right, in here in this problem, comes in this kind of hockey stick form, which, by the way, resembles very much the ReLU function. That's not a coincidence. It's also a useful feature to keep in mind that will give us approximating power as well. Okay. So when you set up your problem, you might want to keep in mind whether the structure of your problem fits into, the form that be easily or friendly to a neural network or particular activation function class. All right. So just kind of put some numbers on the table. What is the level of the challenge of this problem? Depending on your perspective, you may or may not think this is a challenging problem. This is a problem with 4 observable states, 1 hidden state, and then 8 parameters. Right. So in terms of if you count the parameters and the states together, this is a 13-dimensional problem potentially. So by any kind of a traditional metrics, this is a quite challenging problem. I would say at least until 5-10 years ago, this was a problem that people really struggle with in terms of doing serious estimation about. Now, calculating the value of these options is not a problem, right? So in the literature, people have figured out that evaluating expectation of this form, you can do this pretty efficiently using something called the inverse Fourier transform, the conditional characteristic function, something that I'm not going to get into much detail. This basically just says that there is a way effectively to calculate the true value of this function at a reasonable cost. Let's not say that it's cheap to do, but you can do this at a reasonable cost. Okay. All right, so I'm going to just try to dream up some potential applications that I think will be interesting. Right? For example, I might be interested in applying this model to the cross section of, let's say 1,000 stocks. I'm making up. I don't know exactly how many stocks individual stocks have options available for trading, but let's say 1,000 of them. And I want to estimate, right, the model implied, or you can say option market implied jump risk measure for these individual stocks. Right? Now, this is something that people have to try to construct using direct measures of stock returns, right? So calculating, for example, skewness of the returns, and then shown that those measures have interesting properties. For example, they predict the cross-section of stock returns. I'm not going to emphasize why that's interesting, but potentially it could be actually open up doors for different kind of empirical questions you can ask. That, if you think about it, actually is quite challenging problem to do, right? Estimating this model for one option, let's say the index option on a daily basis, is already a major undertaking. Imagine opening up the doors to estimating this for a panel of options on a daily basis. Okay. All right. Next, we might be interested in assessing the kind of degree of a parameter instability. So why is that interesting? Well, you know, think about this model here, the way both academics and practitioners use them is somewhat kind of a schizophrenic, because we kind of view that this model has these parameters in red, right, that are constant. But in practice, the way we use them is we actually fit them every day to a new set of options so that we can recalibrate the model, so to speak. Right? So there is actually a kind of embedded internal inconsistency there. And you know, there are several issues with this. One is that, you know, that just basically means that the model going from one day to the next, you can quickly reject the assumption that the parameters are constant. But another more practical consideration is that for people who are using this model to do things such as delta hedging, right? Those of you who are interested in or are familiar with this concept of delta hedging, basically this is a way for, say, option market makers to synthetically create option positions by buying and selling, you know, stocks and bonds. And they need to know how much to buy and sell, and this is these like Greeks, the deltas, are helping them, right? Now, if you're generating the delta from a kind of an inconsistent model over time, that's quite problematic potentially. So that would imply that there could be implications for how options are actually priced in the data, as well as how market makers would operate. I'm going to show you some empirical evidence interesting related to this. And the third thing is a more kind of a traditional way of thinking about how would you actually accurately test the out-of-sample performance of this model. Right? You might think seems like a pretty you know, a simple question to ask, but to do it right, again, you have to respect the fact that you know, for the model to have the best chance of succeeding, you again have to refeed the parameters over time. So this again involves a lot of kind of re-estimation of the model on a frequent basis, so that you can always look ahead in a one step ahead, for example, to see the true out-of-sample performance. Right? We can keep going here. You know, for example, you might be interested in testing whether this model not only prices the option price, you know, generates small pricing errors on the spot, but also can is it capable of matching the empirical distribution of option returns. Right? That basically means that potentially, or the same question in the last part here, you're calculating the value and risk of a option portfolio. In both cases, you're trying to calculate, right, some kind of distribution of option returns, and typically this is done through simulation. So you're going to have to basically simulate all the potential paths and calculate the option price on those paths. Now, what do all these potential applications have in common? Well, they have in common in the sense that they are very kind of demanding in terms of repeatedly evaluating this model. Right? So if you think that the pricing a set of options for a particular set of parameters is no big deal, now we're basically asking ourselves to repeatedly doing this many, many times, and potentially, you know, really ridiculous large amount of times. That basically presents a computational challenge, and this is why we think potentially it opens up the door for something like a deep surrogate model.
Did you explain to everyone what a jump risk measure is?
Yeah, so that's a good point.
Then I won't interrupt again. Don't explain again to me things you already explained.
No, I haven't actually. So I think this is a good point. That people have been, I think it's 9 o'clock in the morning, so people have been kind of nice.
I wouldn't have known even if it were 10 or 11.
Yeah, well, it's actually 3 a.m. For people from East Coast in the US. So actually, but yeah, I should.
Another question.
Let me get to the jump risk part first. Right? So basically, what I meant by this is that you can fit this model to, say, a cross section or a panel of options, right, and then back out what the parameters, right, all these things highlighted in red, that matches the prices we observe in the market the best, right? So that will basically give you a so-called market implied measure of whatever you want. For example, it could be about the volatility of the volatility. This is what the sigma is. What I meant by the jump is basically referring to this intensity, lambda, of these Poisson arrival of large changes in the price. And in particular, we might be interested in the downside of jump. Remember, this is the double exponential distribution of the jumps. So we're particularly interested in these kind of downside jumps, how big they are, how frequently they happen.
Okay, slow down, because I think 80% of the people in the room don't understand the stochastic difference.
Yeah, feel free to ask questions.
This is what I meant when I said continuous time models cannot match transitory income shocks. Mm-hmm. And 80% of people didn't understand that.
Yeah, by the way, there are models written in continuous time that are specifically trying to address these kind of transitory shocks, but they have to require.
Then you lose all the advantage of continuous time because you don't have this sparse matrix.
Yeah, well, No, not entirely, but it does require additional techniques.
But
Can I stop in here? Sorry, we're not at the conference, so let's.
Okay, that's fine.
No, it's okay. I think this is important for the students to know as well.
Right.
They are, for those people who care about transitory shock, there are indeed additional techniques can involve, but it's not going to be as straightforward as this one.
Right,
These
somebody
are
actually does come to the process in the front.
Can I just interrupt you? So it's about generic estimation technique. So
Yeah.
what's
So the main point here is that this is a problem that has, a lot of state variables and parameters, and evaluating these once may not be such a big deal, but you might have applications you're interested in that requires, many times evaluating, right? So, okay, and by the way, I didn't even put on this like a very generic exercise, which is structure estimation. Right? All these exercises basically are asking for repeated structure estimations.
Mhm.
That's what kind of brings up the challenge of this problem at another level. Right? I hope that point is clear. All right, so let's just kind of put some numbers on the table here. Is kind of a back of the envelope calculation. So those of you who are hardcore numerical computational experts, don't give us a hard time on these numbers. These are pretty crude estimates here. So imagine that you have a 4,000 options on a typical day, and you want to fit this model, right, to this 4,000 options. So you might start by thinking about how much will it take me to price these options. Right? Let's take the kind of the state-of-the-art implementation of the fast Fourier transform. It would take you, on a typical laptop, not supercomputer, about 10 seconds to do this. So you think, no big deal, right? This is a lot easier than many of the problems you might be interested in working on. But if you want to do an estimation, let's imagine that involves multiple rounds of iteration, then the number starts to add up. And imagine that you have to estimate this for just 1 second, for 1 year worth of data. So every day we estimate this, so you can construct a time series of these option implied jump risk measure, for example. Now you're looking at in the hundreds of hours. Yes.
This must be like approximate number.
Oh, very crude.
Okay.
Yes, indeed. Yeah. Of course, you want to really benchmark this, you have to tell me what specification of the computer and so on and so forth.
Yeah, and how many times?
Exactly. Okay. All right. So at this point, you might be thinking, okay, is there another way to go about this? And the answer is so yes. And in fact, it's something that we are familiar with, right? When growing through your early school years, you know that we work with lookup tables. So for example, if you have to evaluate a integral of this form, you wouldn't try to do it yourself. Maybe you have done it before when you learned the numerical integration, but typically in practice, we don't do that, right? We don't try to evaluate this ourselves. In fact, we just look up the normal table, right? You find out what the z value is, and then you find out what the corresponding CDF function is. Done. You trust these numbers, why? They're done very accurately, and then you probably cannot do better than this. So let's just go with that, right? Now imagine, for something like a model, like what was presented over here with potentially, I guess in this case, 13 dimensions. Is there a way to create a lookup table for that too? And the answer is yes. In fact, that's where these deep surrogates come in, right? So this is a picture that you saw yesterday. I apologize if you can show that again. Again, you just be thinking about this is a black box, right? These are the parameter states, hidden or observable, mapping into these outputs over here, could be potentially high dimensional. There is a lot of machinery happens in the middle that does this mapping, but I'm not interested in learning exactly what the mapping is. I just want to have an accurate representation of this mapping. So what I want to do is I want to basically replace that function, right? That's predicted by our economic theory by these very expressive mirror network.
What's the difference between a lookup table and an interpolation method?
Well, interpolation method requires particular assumptions, right? In how you kind of connect the two dots. Here, I guess in some sense, it is also like that. The assumptions are kind of embedded in the structure of the neural network.
But
so it is in some ways an interpolation.
It's a real number, so you can't have we can't look up an infinity of continuous. So what do you?
It is an interpolation.
It is an interpolation.
So you could, in plain English, it's a surrogate. It provides.
Yeah,
it is an interpolation.
Yes.
Right, but
okay.
But it's a bit
in
more
principle,
size. Yes.
Right. Sorry. Exactly. So in principle, you could potentially, right, extrapolate using these function family to regions you have never visited before when you're sampling, right? So then you basically have to put more faith on the functional form you're using here to say that the extrapolation actually will be reliable, which is going to be, I think, potentially quite questionable. Wouldn't recommend to do that. But for the regions where have good handle in the sampling, and relying on the continuity of the function itself, then you can have some good confidence on the accuracy. In fact, that's what we're going to talk about next in terms of how you can actually build some faith into the accuracy, which is a very important thing when you put a lot of hard work into this kind of methodology. Okay. All right. So just give you some taste of the computational savings with the caveat I gave you earlier in mind. If you use a deep surrogate for the same set of tasks, you can save your time by orders of magnitude, right? This is actually without even using the GPU. If you take into the fact that these neural networks are particularly friendly for kind of a parallel computing, you can really drastically save your amount of time. So by the way, the kind of tasks that I kind of dreamt up earlier in that slide are the tasks that will be computationally infeasible if you're using traditional methods, but now they become completely available. So they really opens up the door for completely new ways we can actually study and potentially deploy our models, right? Which is, I think, potentially quite exciting. All right, so I'm going to now talk a little bit more about the kind of the machine learning theory side in terms of in what ways can we actually put faith into these kind of deep surrogate technology, or more importantly, when you should be more kind of cautious or suspicious about their ability. Okay. So I'm going to kind of first set up the problem a little bit just to make the notation clear. So again, I'm going to draw from what I discussed yesterday. So imagine that a economic model can be represented by a set of restrictions between the observable variables S, hidden states H, and some endogenous quantity Y. If you're worried about the potentially endogenous quantities are observed or connected to this variable with error, so then you can replace this Y by expectation. It's kind of what we witnessed question yesterday. And then you have some parameters of your model, which is p-dimensional. Right? So we're going to replace this whole thing by another function f of x, in particular collapsing the set of states, hidden or observable, and the parameters together into one vector x. So these are the inputs. The reason we want to do this is really we want to find a kind of a global representation of the model, right? Not just for one set of parameters for the solution to be, but rather for all kinds of reasonable parameter combinations. All right, so this, of course, is a mapping between something that is, say, again, in our example, is the 13-dimensional to something that is 1 dimension, but it could be potentially, Y could also be high-dimensional as well. By imposing a hierarchical prior on these parameters, right, together with the draws on the x and the distribution implied by the model you write down for x, then you can get the joint distribution of the x and y. And this is where you're going to try to draw the training data from. Okay. All right. So ideally, what we want to do is try to solve the following problem, right? We have some loss function L, and we want to find a function f in the set of all possible functions that map x into y, such that can minimize this expected loss. So for example, we can put in mean squared errors over here, which is the mean squared pricing errors, right? This is the predicted option price. This will be the observable option price. And, not observable, but the model generated option price. And you're trying to minimize the gap between the two. This problem is intractable. Sorry, I should have mentioned first before I go there. In this particular case, unlike in the standard machine learning exercise in practice, we actually know the true data generating process, right? So you don't have to put in a f hat here at all. You actually know the solution to this is f. Okay. All right. So when we try to actually build the deep surrogates, now we're basically committing ourselves to a particular set of functions, right? A particular family, which is this family of neural nets. So let's replace the space of all functions mapping x into y with the space of functions that are deep neural nets. So this is the h, currently h over here. And then we're replacing the expectation over here by this empirical average. Right? So these are two things that you have to do in order to operationalize this procedure. And that solution, if you can find it accurately, will be this f hat of hs. So, Professor, yes, please.
Yeah, what I don't understand is the why is you say we know why.
Yes.
Is it because it's easy to find the value of the option, but not the underlying structure? How do you know the value of the option if it's hard to compute?
We can compute it. It's just that it's computationally demanding. You have to do this many times. Yeah. So yes.
So you start with the computational demanding task of computing data.
So I'm gonna get to that exactly the procedure. So just bear with me for a
So
second.
it is known.
It can be known. Yes.
Into the
Yes. The cost is not zero, but it can be done. Yes. Yes.
Could I ask again, what is the, I'm not getting what the difference is, why this isn't just yet another maybe very useful method of interpolation? Why isn't it just?
You can take it that way. That's totally fine.
Is it just another name for interpolation?
It's a fancy way to do interpolation, a powerful way. Yeah, I'll compare.
That's so helpful. That's so helpful.
Oh yes, absolutely. If that makes you comfortable, in fact, we're going to try to compare other methods that perhaps you're more familiar with in terms of doing
But
interpolation.
it's just another method of interpolation.
Yes.
Oh,
yes. All right. Very good. Okay. So, and this is just a little bit side note on what the network structure will be, right? So you will involve some. Well, the way to describe this network involves some activation function, which could potentially be allowed to be different layer by layer, but in this case, it's represented by sigma. And then the architecture is typically described by the number of neurons in each layer, right? So it starts with D, in this case, 13 neurons for the inputs. And then in the end, you have to come up with K outputs. So these are the dimensions of Y, right? And then the parameters are going to be these matrix of W, which oftentimes are written as the W for the loadings on the previous layers of neurons, and the bias terms over here.
Can you share some tips about choosing architecture? Since you work a lot on these, do you have?
Yeah, so we're going to talk about that a little bit later. So hopefully give you something that's more theory based, and then we're going to talk about some practical experiments we have. Okay. All right, so this is one thing I think is kind of important to kind of appreciate a little bit, which is what are the things that could go wrong, right, when you do the things I just described, right? So imagine that in the end, we want to find this f hat, which is in this case known to be f, right? We know the true function, potentially. And this is what we're going to end up with when you go through this deep circuit training procedure. And there are a few gaps that kind of constitutes a kind of a upper bound on the errors of the approximation. So let's start with the difference between here and here. Right? The difference between this one has a star. This is basically the results of training your neural network and finding some solution, which is not the same as the true solution to this problem over here. Right? This just has to do with the fact that these neural networks have so many parameters that there's no hope of finding the global minimum of this problem. You're going to stop somewhere that you think is good enough. And that's going to present a gap that's oftentimes referred to as the training error. And we're always going to be living with that. Hopefully the training error is not going to be that large, but it's something we cannot get away with. The second thing has to do with the estimation error. This should be relatively easy to understand because you're replacing the true expectation by the empirical average, right? So that is where the estimation error comes in. So the hope is that the law of large numbers can kick in, that this will be a very good approximation. And then the third thing is the so-called approximation error. Right? This refers specifically to the fact that you are searching within a subset of all possible functions to map from X to Y. This is what this blue box here, or purple box, is representing. And the fact that these class of functions may or may not be powerful enough, right, to capture all the interesting features of the function, that's where this approximation error comes in. So this is the first thing I want to talk about next. Yes.
I'm sorry, I think I'm misunderstanding. In this first step, are you searching across the space of architectures like activation functions?
In principle, you could, but in our particular application, we will not. So we basically commit to a particular architecture and then search from there. Yeah, you can do hyperparameter search in that sense, but you will add another layer of the computational challenge.
The different architectures like would better handle discontinuity.
I'm going to talk about that in a second. Yes, this is something very important to keep in mind. Yes. All right, approximating errors. Okay, so I'm going to talk about this part. So first, right, there is a very kind of a reassuring result, a famous result in the deep learning theory, which is this so-called universal approximation theorem. So to already kind of address to your point to some extent, that we start with functions that are continuous, first of all, right? Mm-hmm. And then if you're working with the continuous functions, then basically there always exists a shallow, and shallow is defined as neural networks with one hidden layers, okay, only one hidden layer, but potentially very wide in terms of number of neurons you can have in that layer. such that, you can get this infinity norm here for the error to be as small as you want.
So this is like the virus stress theorem.
It's very much related, yes, yes. In fact, the proof of this line of work is very much drawing on the virus theorem, yes. So there are some classic references on this, okay? But I want to point you to some recent developments in this literature, which basically generates sort of a dual to this result that we had earlier, which is basically that the same universal approximation theorem applies to deep networks. Okay, so you basically can find neural networks with fixed width or upper bound on the width anyway, and unrestricted depth, such that you can achieve the same approximation accuracy. In fact, I'm going to come back to this a little later in terms of the pros and cons, more of the pros of using a deep network as opposed to a shallow network. One thing that actually was showing up in this literature, just a second, is that the required depth has to be at least the depth of the input layer, right? So you should not at least have, in this case, 13 or more for each hidden layer. Yes?
I have a question about the activation function. Is it important for the theory, or what's the activation function? The theory is probably.
It is very much important for the theorem. Yeah, I'm going to talk about that in a second too. Yes. All right, let's keep going. Right, so that's basically addressing this issue that just how powerful these functions are. So they're very good working with continuous functions. So if you have a lot of discontinuity, unfortunately, right, there's just no free lunch. Okay. Yeah. So the whole idea of interpolation works when you work with continuous functions. The Weisner's theorem is based on polynomials with continuous, right? So these all kind of come together.
Got it.
All right. So the next thing is just as important, at least for practical purpose, is that when you build a neural network like this, we know that they are like very data hungry, right? So it is very important to get a sense, right, for what kind of function families, the complexity you would expect to need to achieve, certain level of approximation accuracy. And perhaps goes hand in hand with this first point is the number of observations or training sample you need to generate to be able to deliver that kind of accuracy approximation. Okay, because like we just talked about earlier, you can generate these training samples with some hard work, but they're not free. So if the demand for training sample is so outrageous, this becomes not so much of a good proposition anymore. Okay. All right. So we're going to represent the number of total trainable parameters by this P over here. Right. This P is going to be a function of the architecture you have, which should be pretty straightforward. And then the kind of the general results about this, in particular, apply to any kind of a continuous functions in particular, but also to functions that are more smooth than just the general continuous functions, is typically the result that these number of parameters grows exponentially in the dimension of your inputs. Right? So this is the traditional notion of the curse of dimensionality shows up here in terms of the training these approximation functions. Right? Just for reference, again, I think it's very good to think about these kind of interpolation exercises. So what would you do? What would you have done if you were just trying to build like a very simple, naive approximation using interpolation? Well, you could build a Cartesian grid on this function, right? So imagine that on every dimension you choose n points, then you're looking at on order of n to the d, kind of a number of grid points you have to evaluate in the hard way, and then you can interpolate anywhere in between these grid points, right, using whatever spline functions you want to do, for example. And this obviously is growing exponentially indeed, right? So in general, the way to think about it is that the number of parameters you need grows in the order of epsilon to the power minus d. That's kind of the notion of this exponential growth, right? Well, but here comes the a little bit better news. The better news is that with additional regularity assumptions on these functions, typically having to do with imposing further smoothness of the function family f, as well as potentially imposing some special structure, such as they're maybe embedded in a particular way, this kind of a hierarchical structure. Again, mimicking hierarchical structure that you saw in the neural networks. Then you can get the surrogate to get accurate approximation with potentially substantially lower complexity as well as fewer number of observations. So I'm going to point out one particular example, which is obviously communicating a perfect fit for our particular application shown here, but it does give us a way to think about more systematically how you would choose the kind of problems that are more suitable for this purpose. Just 1 second there. Okay, I'll get back to your question. So let me just kind of walk you through this quote unquote result theorem here, and then we can talk open up the discussion. All right, so the result is the following, right? So a deep neural network can overcome the curse of dimensionality when approximating the solution to a d-dimensional Kolmogorov equation with affine drift and diffusion. Basically, a linear Kolmogorov equation can essentially be approximated without the curse of dimensionality. So in particular, M, which is the number of the size of the training sample, and P is the total parameters, right? Both of them are capped at polynomial growth in terms of D. Right, that basically says that your training sample is going to be potentially quite a bit smaller than what the usual neural network would require, or a function class would require for you. And that's good news because you're not going to have to pay so much of the upfront cost to generate a large training sample anymore. Right? And here is a little bit intuition. I'm not going to get into the details of why this result is valid, but just give you a little bit intuition for why that's the case. So first of all, right, the solution to these Kolmogorov equations can actually be conveniently represented in terms of expectations. This is for those of you who are have worked with these kind of a stochastic calculus or option pricing problem. This is due to the result of Feynman cap. Okay, so the PDEs can have this kind of deterministic PDEs can have a stochastic interpretation. You're basically imagining that you're calculating the expected terminal value of some function of some stochastic process, right, which looks just like these option pricing model I showed you on the first slide, right? You're basically having some multi-dimensional stochastic process that describes how the underlying state evolves. And your function ultimately is trying to calculate what is expected value of some function of that underlying state at some terminal date cap t, right? You just maybe go back and refresh it for you. This is what I'm talking about, right? So these are the state variables that evolves over time, and your function ultimately is the expected value of some terminal value. This kind of form actually applies to many problems in economics, right? So when you're basically calculating, let's imagine your value function is basically expected integral of your utility over some finite horizon or over some interval, I should say. Effectively, this will be suitable to be represented in terms of the expectation form. Why is this important? Because this is actually the same thing you're solving in the statistical learning problem, right? And when you try to build the neural network, effectively can be thought of as a expectation of some function f that is hopefully close to the y, depending on the loss function you choose. If you're choosing mean squared error, then you're basically trying to find the best forecast, conditional forecast of y given the set of features x. This is exactly why the problem is potentially friendly for neural networks. And the second thing has to do with the terminal value, which is related to this activation function question. Right. So in the case of option pricing, I just showed you before, the terminal value is a function of the underlying state in the hockey stick form. So that's exactly what we'll be using if you're using something that looks like a ReLU. Right. So ReLU would be this hockey stick, or something that is close to, but doesn't have to be exactly. All right. So now it's time to let's open our discussion.
Two questions. One is just you said regularity conditions, so like concavity and monotonicity, things like that.
That is okay. Yes.
And those are fairly easy.
Yes, that's okay. It's basically about how how smooth it is. For example, the first, second, third order derivatives, are they smooth, and whether what order of integrability they are. Right? These are the regularity conditions.
Okay. So second question or point is there's something called a method of parameterized expectations that's widely used in macro model. It sounds very much like you're saying, okay, the neural net has certain parameters, and this is just a particular functional form for the approximator so you're estimating parameters of the parameterized expectations.
Let me think about that. I think in some ways, yes, you can think of it that way. Right? So if you think about these prices we're generating is some expectations, right? You're basically parameterize a function that would represent this expectation accurately.
So it's like the method of parameterized expectations.
Can I just comment? Sorry.
Yeah, please.
You write in this particular solution of like the early work by Ben Hahn. That would be a subset that would be so it entails that one, but this.
Yeah.
Yes.
Yeah, but I'm just trying to
Yeah,
understand.
conceptually, you're right. For this particular type of applications, you're right. This is just more general. So like, it doesn't rely on expectations. So if you have like say a non-stochastic growth model with which is non-stationary, with parameters, you could still do the same thing. There's no expectation anyway.
Yeah. I was just trying to relate it to things I already understand.
Yeah. Okay. Yes.
Yeah, okay, so, yes, please.
So as somebody who's like pretty unfamiliar to this, and has some familiarity with the existing methods, I see there's like a lot of really cool benefits to it. Are there reasons not to use this in a
Yeah,
simple?
we're gonna talk about that, although, we're gonna be obviously a little bit biased, but, we can definitely have a discussion about, how do you compare the alternative method. This is gonna be a very important point. Yes. So I just want to kind of make sure emphasize one more time what can draw on this, right? So of course it's difficult to kind of expand the kind of these type of results too broadly, but I think there are two very valuable lessons we can draw from this, which is that when you think about using deep neural nets to approximate the kind of problem you're working with, the first thing is that if the problem has already this feature that kind of basically can be easily translate into a expectation of something that it can be represented by a stochastic system, then you have a good hope of fitting into the first category. And secondly, when you're choosing the activation functions, keep in mind what the kind of terminal function looks like, right? If you are, for example, calculating some kind of a utility functions expected values and utility functions of underlying states, perhaps keep that in mind when you choose the activation function. Can actually save you in terms of the accuracy and with a lower degree of complexity of the model. Okay. All right, so let me keep going over here. So there are some other things that can be actually useful in guiding us in choosing these neural networks. First one is this result that the ReLU networks, which has been quite popular, actually struggles with some simple function class families. So example, for something like a quadratic function like this, it is actually quite not trivial to try to have an accurate approximation of something that is as simple or seemingly as simple as this with the ReLU family. You will be actually better off using a activation function that is second order continuous differentiable. And there's some references on this, and this is actually one of the reasons that drive us to choose not the ReLU for our application, but rather the switch function we can talk about later. The next thing is the depth. Right? So this has to do with essentially comparing deep versus shallow networks. And this is, again, a well-established result that there are indeed unique advantages using deep neural networks compared to the shallow ones. In particular, more complex shallow networks might be needed, actually far more complex shallow networks might be needed to obtain the same level of accuracy as a deep network. Right? So given how easy now it is to train a deep network, I think probably it's better just to go with the deeper ones. In fact, with the recent kind of uptake of the resonance, you can actually train potentially much deeper networks much more easily compared to before. Okay. All right, so now I'm going to kind of take a step back and now kind of step away from this approximation power or expressivity and the cursive dimensionality to some of the more generic benefits of these deep networks. Right? First of all, in thinking about the methodology of deep networks compared to some other potential machine learning methods you might be interested in using, right? It's undeniable. This goes to one of the drawbacks is that the deep neural networks are very data hungry. Right? So you need to. There's no way of getting around of generating a large training sample for this. So what kind of application would be beneficial or sensible for building a deep surrogate for? Well, it better be that producing a reasonable large training sample is not inhibitively expensive. That's prohibitively expensive. So this should be an important consideration. In fact, feel free to jump in, Simon, by the way. For some other kind of application where generating training samples is in fact quite difficult, you might want to switch to something like Gaussian processes, right? So that's where actually you can get reasonable approximation accuracy, but doesn't have to be so kind of demanding in terms of generating a training sample. Another thing that I should mention is kind of interesting feature is that unlike in this kind of standard machine learning application you would be working with, here we know the true model. So for one, we can in fact, right, if you can afford it, you can actually generate potentially unlimited data up to some kind of a computational resource challenge budget. And you can do this at essentially very low or close to no errors. Yes.
Just to make sure that I follow. So in your particular application, like training, like elements of the training samples are like a particularly draw of like current states and parameters, and then you solve the option pricing problem for this, and then
there's
like,
no
the results.
that step has no magic, right? You basically do it the hard way. Whatever your favorite or most efficient method for solving the model, you apply it there. There's no contribution for us on that step. But once you generate the training sample, now let's build a lookup table for exact that mapping.
And can I just, sorry, and my apologies.
No, feel free.
Remember, this thing is 13 dimensional. So like, what you typically do is in the dumb old way, you would say you have 100, because you will see this is a highly nonlinear functional surface not approximate. So like this, you would need, say, 13 dimensions. Say you put just 10 points in each direction, right? You'd have 10 to the 13. You have, when Louis says we produce a large amount of points, yes, that's true, but we talk probably millions, hundreds of millions. But this is still 4, 5, 6 orders of magnitude less than what you would do for
Yeah, so that has to do with this curse of dimensionality discussion we just had earlier, right? So even though, in some special cases you can overcome the curse of dimensionality, that doesn't mean you don't have to pay the cost of generating a large sample, right? So anyway, so okay, where was I? So I was talking about essentially this point that because you can generate the mapping between X and Y in a way that is close to being error-free, hopefully the implementation is good enough. That means that these usual concerns about overfitting actually, doesn't entirely apply to our setting. I wouldn't say that we're immune to overfitting issues, but it's actually largely free of that concern. Which is why this notion of it's kind of a recently discovered phenomenon of double descent empirically actually really makes sense for our setting. What that means is basically when you train these neural networks, you can actually run large number of epochs, right? Just run through your data again and again to really get a good representation so that this training error that I was talking about earlier can actually be further reduced. Right? That's one kind of practical guidance. Yes.
So when you say we know the true model, I think I'm still a little bit confused.
Yeah.
What exactly do we know versus not know here? Like, we're still estimating parameter values, right? Or are we not even doing that?
We're not even doing that. We're drawing state and parameters together. So we would know in any incidence what the true parameters would be. Right? And then we do the mapping between those and the output.
Okay, so then we're basically constructing a surrogate or some sort of like approximation to the true model. Because like essentially why, I guess you're saying because it's hard to basically plug X into the true model and spit out Y. So you're constructing a surrogate, but like why is it hard to just plug in X and get out Y in the true model?
Conceptually, there's nothing hard about it. It's just computationally, it's costly if you have to do this many times.
So this is only for like certain types of, because I feel like for a lot of models, like once you know the parameters, you just plug it in and it spits it out.
Oh yeah, once you know the parameters, you're assuming away essentially the problem that we're trying to solve. Right. A lot of times empirically, we're trying to estimate the parameters, and in the application we're talking about, many times you have to estimate the parameters again and again and again. Can I imagine that you have, just one second, you imagine that you have like I'm going to use an example in like say household finance, right? So you would have kind of a cross section of households who have their consumption portfolio problems they're facing, and you're interested in learning heterogeneity across the household in terms of preferences or constraints they're facing. So now you basically are not only having solved a potentially pretty complicated life cycle consumption saving problem, but you also have to apply this or estimate this on a large panel of households. You basically need to estimate this again and again for a really large.
You need to estimate the time preference rate, let's say.
Potentially, yeah. For example,
you solve for different values of the time preference rate, and you have the solution for beta equals 0.99 and beta equals 0.98 and beta equals 0.97, and then you just interpolate for you need to the search method is you need to look for 0.95, 0.9985, or 0.987 or something. And you've got the solution for 0.99, you've got the solution for 0.98, and it's just interpolating in between.
Okay. And I guess it's just like this is applicable for certain types of models where it's just, I guess, hard, but it's hard computational to solve it for a specific X.
Yes.
Okay.
And you have a need to repeatedly apply it.
Oh, okay. So there's probably what are these like different? This is probably it's like a differential equation or something where it's like
it doesn't have to be hard. Yeah. But yeah, so it's important to know when you need it and when you don't need it. Hopefully I made that clear, maybe not, I guess. So yeah, you need a problem that is non-trivial to compute, and you need to deploy it many, many times. That's the setting where it is.
Can I give an exact definition when you should use it?
Yeah,
So if
please.
you know, so
Just a second.
you know, when you, if you go to the first day back where when you saw this bus model, right? So when you do structural estimations, you have essentially for a given set of parameters, you solve the model.
Right.
Then you see, say you want to match moments.
Yeah.
Then you check if you're close, if not,
Sure.
take a step in the parameter just into okay. Now, solving a model has a certain amount of computation steps, say 100. Evaluating a neural net has a certain amount of computation steps, say 50. So as soon as this break-even point of the computation steps of evaluating the neural net is small, then evaluating the model, we take the surrogate. So evaluating an analytical function as a few floating point approach, we don't care. If we have the solve a dynamic model, you want to interpolate or like evaluate the neural net a few floating. Still, it's a huge sum, but this sum is much cheaper than.
I will actually do some like a comparison to argue that the trade-off might be even more beneficial than thinking about individual basis, because in a way, you think about the normal table we built, right? It's a public good. You're building it once and building really accurately such that everybody can use it. So it's actually saving a lot of public resources. Okay, question.
Yeah, so in practice, you probably need some sort of wide support of the parameters, the structural parameters, right?
Yeah.
And the wider support, the more crude the approximation would be.
Correct.
So would you usually do one, like say you do for the crude, do it once, and then you get like a approximate solution. Now now you can shrink the surface of the structural parameters and run it again.
Yeah, so I'm going to describe the procedure we use. Certainly, I'm not going to argue that's the optimal one, but I think there is indeed a lot of way you're thinking about how to do this, notion of active learning to make this process more efficient. Yes.
What if the output of the model is really complex and high-dimensional, like in a macro model, where the output is transition paths from multiple variables and distribution, equilibrium kind of distribution transitions? How good are these models at taking the forecasting all those high-dimensional outputs?
Well, I think it depends on exactly what you mean by high dimensional, right? So that when we mention the transition path, again, it's a little pause, but if the Y itself is more than one dimensional in general, then it's not a problem for the neural network to map the vector X into a high dimension, a multiple dimensional Y. So, but if you have to actually explain some kind of functions of the transition path, that becomes a different issue. So when you're thinking about a way to parameterize a function that kind of describes a very flexible transition path, that potentially could create a problem for us. I think I should get going, but I'd be happy to take more questions because I have until what? 20 past. So okay. But yeah, it's not I don't appreciate the discussion, but I'm sure we can have more time to discuss afterwards as well. All right, so I do want to advocate a bit more on the benefits, right? So obviously, hopefully you can kind of be sympathetic to this, that if you do a good job in terms of approximating this, you would be able to get a high accuracy representation of the function, underlying function. It's going to be a lot cheaper to evaluate once it's trained. So kind of after the training, right, the hard work is done, then using it is essentially free. And another thing that's not to be kind of dismissed is that this becomes actually very easy to store and share. So imagine that your neural network involves, let's say, 1 million parameters, right? So storing this representation basically requires about 20 megabytes of storage space. But if you use the Cartesian grid and the old way of interpolation, now you're dealing with an enormous object that you have to store, right? So for high dimensional problem, you can see the saving here. It's quite obvious. Why is that important? Because now it becomes really important to potentially share with these.
It seems like comparison to the interpolation kind of unfair because that's not how we estimate problems, right? We use estimators, which use the gradient maximum likelihood function. So it's not that we would actually calculate this gradient.
Well, it depends, right? So if you estimate it once, I would agree, right? So you'll be visiting a particular path of the that's dictated by your estimation procedure. But imagine you're doing this again, you're effectively visiting many different parts of the space of X, right? So that basically requires you to have a very good approximation everywhere. So that's where the demand becomes essentially the problem we're describing.
But isn't then also the surrogate dependent on the part of the parameters that I trained it? Like-
Oh, absolutely. Yeah, totally. Yes.
So when we do interpolation, maybe you solve it for x equals 0, x equals 10, and then use the interpolation to get everything in between. Are we actually interpolating here, or do we essentially need to solve for a few different x's to start with? Or can we just immediately start with the neural net, not actually have to solve it for any x individual line?
Oh, we have to get a training sample, right? When you get a training sample, you are getting the mapping from the x and y.
Right.
Yes, those are the points of interpolation.
Okay.
But it's not the interpolation in the usual sense that you don't have to fit those points exactly, right? It's basically trying to find it's kind of like running a regression, that would be the right analogy. You're trying to find a function of particular family that fit this cloud of data the best you can, without binding your hands, for example, using like a Chebyshev polynomial where you fit those particular points exactly.
Okay.
All right, one last kind of advertising here, and I promise I'll get move beyond this class, is that this can really be a public good, can be shared, right? So we have Dynair, which is a fantastic service for the whole profession. Imagine that you have these lookup tables for the workhorse models in economics or finance, right? In this case, we're building one for the option pricing model. That would potentially saves a lot of the nightmare for graduate students and faculty members as well, in terms of building your own implementation of these models, because somebody has done it and done it right, and you cannot imagine doing any better than them. So that's a tremendous save. Okay, so here is
a website that you could all these.
Absolutely. In fact, you give me a way in to talk one more sentence, say one more sentence about this. Imagine how this kind of community would work, right? So typically, let's say Dynair started something like this. Fantastic. Well,
Econometric.
Econometric. Okay, sorry.
This is what we're going to do on Econometric.
Yeah. So imagine that we started something like this. Taking the model we built. Okay. That's maybe not the most exciting application, but let's say that we built that. Okay. So how would you be able to potentially improve upon this model? Well, what's the most expensive part of this whole endeavor? Training data. Right. So imagine that we kind of upload some script, right, computer script that you can easily download, and then in the spare time of your computer, run it on the background and generate training data for us. In particular, sampling the space where so far the model has had a difficulty generating accurate approximations. Well, you submit your training data. That's a big favor to the community, and then we can now basically do this kind of a version of online learning and update the model, make it even more better and better, and share with everybody. So I think in terms of the economic benefits, it's tremendous potential with the right applications. All right, so I did promise that I want to compare the different methods. I'm not going to say this is comprehensive or even fair. I'm going to pretend that it's fair, but I do want to kind of highlight a few things you want to keep in mind, right? So one is in terms of the dimensional inputs. The other one is the local features. We are obviously working with the space of continuous functions, but in some cases you might have discontinuity in terms of the derivatives, or in other more extreme cases you might have just discontinuity in general. So whether you can, what kind of family you want to be
But
using.
if you know where those discontinuities are, you can just build them in, and that will make it enormously more efficient. It's part of the thing you get.
If you know exactly where it is. Yes.
Yeah, if you know exactly where it is when you solve the model in your training thing, you build those particular points in, and you know there aren't any other discontinuities because of the structure of the model, and it can be hugely.
I totally agree. Yeah, and by the way, the deep neural nets actually have no problem handling functions that are piecewise continuous. I think this is actually relatively easy to do as well. Irregularity of the shape of the domain is something that you might be concerned about. And basically, if you imagine that this vector of x comes from some kind of hypercube, then it's opens up the doors to using grid-based methods such as the sparse grid. But otherwise, if the domain is somewhat irregular, depending on the problem you're working with, then maybe those kind of grid-based methods may be more challenging. And also the amount of data. As I mentioned earlier, that if you have generating any training sample is just really expensive, then you're probably better off using something like the Gaussian process rather than the deep neural nets. Okay. All right. So we do have the kind of the usual suspects over here, right? Think about the polynomial-based interpolation methods over here. So there, these kind of local features can be potentially a problem, in the sense that something changes locally a little bit, right? That can have really significant ripple effects for how the polynomial function that you're using to approximate things would behave elsewhere, pretty far down on both sides of the space. Okay, we have more discussions in the paper. You're welcome to check it out. All right, so now I'm gonna use the remaining 20 minutes or so to talk about the example application, which hopefully give you a flavor of how you will be able to implement something for yourself. Okay, so we're gonna build the deep surrogate for the two versions of the kind of the option pricing model, which are very commonly used in the finance settings. One is the model that I presented at the beginning, the base model of the double exponential jumps. The other one is the Heston model, which is the stochastic volatility model without jumps. Okay. I'm going to try to do some empirical analysis with the surrogate model to just kind of flash our muscles and show that we can do this. And there's some additional interesting results from that, but that's not the key point of this. Okay. All right.
What is RF? R of sample RF, what is RF?
Oh, sorry, ignore that. This is basically, in that paper, we try to do a horse race between these structural models with a reduced form model. In this case, reduced form model we're using is random forest model, which also is RF.
RF reduced form.
Yeah. Okay, let me keep going, but that's irrelevant for the topic today. These are kind of the economic message from the application, but that's not what I want to emphasize. Okay, so we're going to see how we're going to be able to apply this right to the problem. All right, so again, just remind ourselves the objective is to find the approximation, right, a surrogate model that would be kind of hopefully truthfully representing the mapping between the input and output of the function over here. It should be highly accurate, and once it's trained, it should be easy to evaluate. Right. So there is immediately a question, right? So you can imagine how we do this. We first need to do the hard work of generating a training sample. The immediate question is, what is kind of the optimal way of sampling? I'm going to show you first our dumb way of doing this, which is basically just uniformly draw from this happy cube. But there's a lot of thinking potentially. The suggestion about active learning is a fantastic one, something that we have not explored enough, but it's certainly something that's on our to-do list. The next thing is, when do you know you have a model that is good enough, right? So you need to be able to evaluate the network you built to kind of assess truthfully the accuracy you can deliver. So that basically requires you to kind of estimate the kind of approximation errors in out of sample sense. Yes.
Bit of a like that. Maybe it's like a bit more general question. Like what I'm wondering here, I feel like in economics, a lot of models have like the property of you have like for a given solution, you have like for given parameters, you get a solution that you could apply for like many states. For example, maybe your model has say state-based representation, right? So also for a given set of parameters, evaluating the output for like new states becomes like
that can be done
like very cheap. So is there some kind of so that I guess should like affect how we should like sample for like states compared to parameters, right? So like, do you have some kind of idea like how many? I mean, obviously it will depend on the model, but whether you have like some kind of vague idea like how important it is to sample from one thing versus the other, because like sampling from one part is much cheaper than.
So I'm going to kind of interpret your question and tell me if I'm wrong. I'm going to interpret your question in terms of the last category here, which is basically that there's some theory guidance on what is the optimal way of sampling, right? So intuitively, when you're trying to build a kind of interpolation of a large object over here, you know that you won't need to sample so heavily if the function is very well behaved. Let's say, it's linear or the derivative doesn't barely change at all, right, in some region. You just need to pick the 2 points at the end, you're done. But if the function is like zigzagging, well, not exactly zigzagging in a discontinuous way, but it's like the derivative is changing around a lot, you know that in those regions you have to sample very heavily. So I think that's the way I would interpret it.
Just based on the curvature to draw the estimate, if you want more points where there's more curvature.
Potentially, yes. So I think there are a lot you can potentially do that will be much smarter than our method, which is this kind of uniform drawing. What we are doing is kind of a data-driven approach, which is basically thinking about, okay, if you sample and you evaluate these quote-unquote out-of-sample approximation errors, and you notice that in certain regions that the performance of the model is really lagging, well, then this is where you need to draw more data. So, and that's another way, perhaps not as efficient way, but a way to discover these weakness, regions where you need to have more heavy sampling. And when you do draw these new data, you would put that into your training set and refit the model, potentially even with a more like a different architecture, right? Adding more layers, for example, more width to the network, and get a benefit that way. And then you can. This is going to be obviously an iterative process. You would basically stop when some kind of stopping criteria has been. Right. All right. So this is the activation function we're using this particular exercise. So you can see that for one, it represents in a kind of qualitative way these kind of hockey stick feature of the payoff function of the option price, which, as you saw in the result I presented earlier, is important for us to get away with the accurate training without having so many data points. On the other hand, it also has the feature that unlike the ReLU function, right, this actually is something whether differentiable continuous at the point 0, unlike the ReLU, which is not differentiable at point 0, and that is important for approximating a function that has these kind of continuous features everywhere. Right. So there might be other benefits, and Simon is going to be the expert on that. So I'm going to relate. Okay, so now here's basically how we're going to be able to kind of populate our training sample. Right? So imagine that this whole input space is hypercube. We're going to just draw uniformly from this. Right? There's nothing fancy about this. In a particular model you have, you might want to embed some kind of correlation structure between the state variables under some certain parameters. Then you might want to use some kind of simulation-based approach. Right? That would respect the underlying correlation structure better. Here, we don't actually have that issue, so we're just going to be uniformly drawn. So, okay. And then with this training sample, right, we just try to minimize the approximation error by training the network. In this case, we're using mean absolute error as a loss function. And then once you have done it, you want to check the accuracy of the approximation, right? So this is where you want to generate new samples. You don't want to run into the problem of using the same sample twice. So we generate new samples of another size j to evaluate the validation error. You would again using these mean absolute error to evaluate this. And if this criteria is met, then you have done your job. So you have to specify some criteria in the first place. But if it's not met, then you want to do it again. So in this is where you have to do the resampling. And there might be various ways to identify problematic regions where you want to sample more heavily and then to replenish your training set. And also potentially change your architecture. All right, so this is the architecture we end up using. For the problem that I showed you on the first slide, this is the 13-dimensional problem. We end up using a very straightforward feed-forward network with 7 fully connected layers, 400 neurons in each. So it's not that deep per se, but relatively wide. So altogether, it's about 1 million trainable parameters. And the surrogate training, so the training sample size is 10 to the 9. Right? So this is not easy task. We actually have to use a supercomputer to do it, to do it efficiently. But compared to, again, thinking about 10 to the 13, which is right, kind of the order of magnitude for.
Can I just say an anecdote? So like the supercomputer, so there was, it's co-authored with a former PhD student of mine who is now at Melbourne, and they had time on the supercomputing to generate these observations, and they learned my lesson there. So like, you know, students super excited, has access to my account. Like anyway, he misparameterized the number of samples anyway, so we burned overnight electricity worth $10,000. So because like, you know, he generated way too much data. But anyway, yeah.
One thing I should highlight is that obviously when you try to generate these training samples, right, it's completely parallel. So you can just do this on multiple GPUs and can be efficient. All right, let's keep going. Right, so here is the one slide on potentially using, once you train it, using this kind of a deep surrogate to do structure estimation. Oh yes.
So here you do a QMM setup.
Oh yes.
Could you potentially take the parameters? So the structural parameters, make a neural network that captures those, just a small subnetwork. Then you add the computational graph when you're training, you don't update those parameters because those are exogenous given, right? But when you want to estimate it, you add them, and then you can differentiate with respect to that subnetwork, and then you can find, like, you can follow the gradient descent. Basically, do you know if that's done or it's possible or?
I personally, I'm not aware. It does sound like an interesting idea, potentially worth pursuing. Yes.
You say a couple of words when you use these 10 to the 9 magnitude training set, like how do you generate it? You start out with like how many, and then like on this, like how big is the set that you have to check your outside error, and then like how many times did you iterate?
I see. This is a question that student that Simon just mentioned would be the right person to answer. You know, the painful procedure. I mean, the process he went through. That. Yeah.
I don't remember the exact, but typically say 10. You know, say if you have 100 points, you use 80 for fitting. Then you 24 out of sample tests, you do not have to do. So we need to start with the 4 million points, which is very sparse if you think of a certain dimension space. I think it's brain that it's literally API parallel. You don't need any skill for programming, except you need to make sure that you check, otherwise it's expensive.
Related question, so around updating the parameters, do all the 80% training data go in, or do you subsample some of the data to train the next?
The way we do it is we keep the original data in there. We don't throw them away.
So each round you have the 80% of the data set, then there is.
We add new training sample to it, yes. But I think now that you mentioned it, I think perhaps what we could have tried is basically put higher weights on this new data, because again, this is the data drawn from region that we have previously lacked in performance. We didn't do that, but again, I think this is where you see that we are basically just trying in a very kind of brain dead way, and there's a lot of potential things you can optimize about here. Okay, so what's the point of this slide? It's basically demonstrating some potential ways you can use this, right? So this is just one example of the extreme estimator that we use all the time. This is a GMM estimator, where you build these kind of J's to this way you're trying to minimize to find a parameter you want to estimate. So now I've changed, by the way, in case you're a little bit lost, we are now changing the question we asked, right? So now we're taking the model we have already built, we built a surrogate for, we're trying to use it in the data. For actual data we observe, we're trying to back out what the structure parameters will be, right? So this will be a very typical problem that you want to solve using this type of model. The nice thing about this is that because now we have near network representations of these moment functions over here, you can obviously take advantage of these back propagation and automatic differentiation kind of techniques to evaluate the gradients of these statistics very easily. So effectively translating to this kind of a minimization problem in terms of a system of nonlinear equations, which may give you some additional savings in terms of computation. Yes.
Sorry, please correct me if I'm wrong. But an alternative to doing this, if I want to do structural estimations, would be instead of making it learn f of x theta equal to y, make it learn theta equal to f of xy, if I know the models, right?
Isn't this one of the papers that was done like 2 days ago on the conference, right? So basically, is that what you meant? Like do the mapping differently?
Yeah, do the mapping from the data to the parameters, and then.
Sorry, I forgot the name of the author, but that paper was exactly doing this, right? Just trying to reverse the mapping from the data to the parameters and try to learn.
Yeah. So.
Oh yes, absolutely.
Which one would you recommend if I want to do just estimation? I don't want to do model evaluation. I want to do estimation.
I don't have empirical kind of metrics to back myself up, but my intuition would say perhaps it's more efficient. Just go directly after the parameters. Would you agree with that?
I haven't tried that.
Yeah, because it's hard to speculate, but intuitively we would think that it's probably more efficient just go for net mapping directly. But to keep in mind that this will give you some additional benefits, right? Maybe you don't. Like after a while, you realize you want to do something else besides just estimation.
No, I was thinking if the model is not identified, the structure is not identified, then the first method doesn't count that warning sign, it will do it's almost like calibration, but in fact, some of the structure might not be identified. But I think
that's a very
this
good point.
method will give some sense, whether it's identified or not.
All right, let's keep going. So I'm going to show you some result in the last 7 minutes or so. The good thing is that it's really quick. Just give you a sense how good approximation can be and what the analysis can do, right? So here is basically a variety of the pictures we plot in the paper that just shows the nature of the nonlinearity embedded in this problem. Right? So this is basically saying that when the function you're trying to approximate is kind of non-trivially nonlinear, then the usual kind of simple approximation like methods like the standard like a polynomial interpolation doesn't have a harder time capturing all these local features. And our model does a pretty good job. Our surrogate does a pretty good job. The reason that you saw only one line on each one of this picture is because our surrogate predictions are exactly on top of the true solution for all these different features. Okay. All right, and this is another challenge we throw at our model. So this is we're asking our model to produce the derivatives of the function we're trying to approximate. Right? So these are the deltas and the betas, and basically derivatives respect to stock price and the time. Right? So again, you see one line, which means that even though we did not explicitly have this derivatives approximation as part of our objective or loss function, because our approximation of the function itself is so accurate that the derivatives actually is pretty amazingly accurate as well. All right, so here is something that you will care about deeply if you want to consider using this deep surrogate to do structure estimation. So the nature of the exercise here is the following. We would randomly draw parameters, no longer drawing the parameters, and then simulate data. And then we would take those data as if they're the real data, and we'll go do structure estimation using our deep surrogate model. Okay, and then we check how well do the structurally estimated parameters, in this case using GMM, get to the true parameters. So we're basically plotting the kind of the box plots of the approximation error or estimation errors of the GMM estimates compared to true values. Okay, so you can see that by and large, the approximation errors or estimation errors are very small, which is again thanks to the fact that not only it's approximating the function accurately, but also approximating derivatives accurately, which makes this inversion potentially viable. I would recommend you to do this if you are interested in using this deep surrogate to do structure estimation yourself, right, so that you can know, right, approximating the function itself is good, but it's not sufficient for these type of extreme estimated based methods. So you want to make sure that you can in fact accurately invert the true parameters sort of from the data.
Can I ask a question? So the GMM standard error is going to be affected by the first stage surrogate?
Hopefully not, right? So of course it will be affected a little bit because remember we have these different stages of errors embedded in our surrogate compared to the true function. But hopefully those are small enough that would not contribute a major part of the GMM standard errors. Yes. It's true that we haven't tried actually to bound how big that error would be. That's something actually potentially worth trying. I think in fact, I can give you something even better. From the kind of uniform bounds, like the global bounds on the approximation error that we are getting a approximation of when we check the outer sample approximation errors, you can actually from there derive some kind of bounds on the GMM standard errors, because those will be some functions of these approximation errors. It's an interesting question, but we haven't done it. Okay, so this is what the data looks like. Not that interesting per se, but here's how we're going to apply it to those data. So, sorry, shouldn't have gone so fast. This is kind of the distribution of the data based on the options we have available in the market of different maturities. And this is the average sample size on a particular day, right? So by the last 10 years, on average, we have about 4,000 options per day. So these are the parameter estimates when we apply this model to this panel of, this time series, panel of index options from the S&P 500 index option, and estimate these kind of daily estimates of the parameters. So we're plotting two parameters here. One is kappa, which is the speed of mean reversion of the underlying volatility state. And rho is the correlation between the shocks to the stock price and shocks to the volatility. So you get these interesting plots over here. For example, we can talk a little bit about the economics of this. Basically, this is telling you instantaneously how correlated are the innovations to the stock price and volatility, right? So if there's a well-known phenomenon, kind of the leverage effect in the stock market, which basically says that when the stock price drops, volatility tend to rise. That's pretty well kind of captured over here. There's a negative correlation, but interestingly, you see a pretty substantial time variation of this. So from the option market, you can learn quite a bit about the correlation, how it changes. Perhaps not that surprisingly, you see this leverage effect being particularly pronounced in 2008 during the financial crisis. Okay. The other parameters you can estimate here. So these are now parameters that are germane to your understanding of the option implied jump risk in the overall market. Right, so this lambda is the kind of the jump intensity, and P is the probability conditional on the jump, that jump being a downward jump. So some product of this two will give you basically the probability of downward jumps, and that have changed a lot. And you can see that again, right, in the, sorry, I think P, I must have misspoken. So P must be the probability of the upward jumps, and that's why 1 minus P is the probability of downward jumps. So in the peak of the crisis, you can see the probability of jumps as implied by the option market have really spiked up. Okay, I should start summarizing, I think, actually. So we have various results in the paper. I recommend you check it out. That basically compares the out of sample forecasting errors of these option pricing models. To do it right, really, you want to, again, right, using this kind of a rolling window or expanding window approach. You want to re-estimate a model, predict one step ahead, and so on and so forth. That basically requires to repeatedly re-estimate a model. And that's why those upfront costs you pay becomes worthwhile. Okay, keeping going here. So here we have the out of sample hedging performance. So remember that one way to judge whether these models are any good is basically can they produce reliable hedging ratios so that you can actually accurately reproduce the option using stocks and bonds. Maybe this thing's worth 30 seconds, and then
you can have 2 minutes extra.
it's okay. I think people already got a gist of this. So this one last thing I want to talk about is basically the using these technique to do structure estimation and then get at this measure of parameter instability. I remember that I mentioned at the beginning that these models are somewhat kind of internally inconsistent, right? We are allowing the parameters to change over time, essentially, when we apply it in practice. So this is basically a way to systematically document just how bad is this problem. So we're going to basically estimate these parameters day by day, for example, or at whatever frequency. And then you can actually generate a pretty standard chi-square test to see if the parameters from one period to another are statistically significantly different enough. Right? So this is pretty standard chi-square test you can do. And the question is, can you do this at a reasonably high frequency? Until these kind of techniques become available, usually the best thing, at best what people would do is basically split the sample in half, right? Estimate parameters in one first half and the second half, and maybe do a test between two. Anything more frequent than that is just going to be too expensive. But now, because we have this technique, you can do this as essentially as frequent as you want. So here is basically these average, so number of days with which the model actually rejects the hypothesis that parameters are the same between two adjacent days. You can see that there's some smooth version of this we're plotting, so you can see that there is actually non-trivial variation over time of how unstable the parameters are from one day to another. Right? And this has some ramifications for example, implications for example, things like option market, option pricing and market making. Right? If you are an option market maker and you're trying to produce hedge ratios using some kind of model, and you know that this model's parameters can change very drastically from one day to another, would you trust your hedge ratio? Probably not. And if you don't trust your hedge ratio, what would you do? You probably charge higher bid-ask spreads, right? So there's a kind of theoretically well-founded reason for the change between the two. And that's in fact what we found in the data. But since I'm out of time, I'm just conclude. I hope this is somewhat useful for those of you who are interested in finding more efficient ways to deploy your model, including, for example, doing structure estimation. I gave you some kind of theoretical kind of guidance in terms of in what settings you might find it worthwhile to do, right? What kind of function families and how you would choose your activation functions for those problems you face. Hopefully this will be a useful tool for your research.